Okay, we're going to take a look at some integrals here that are going to have things of the form on the screen, usually with square roots, usually some number minus x squared, a number plus x squared, or x squared minus a number. Okay, they actually don't have to be in square roots, but usually there are. Once in a while you might get something, especially in a squared plus x squared kind of term, and that'll work in a similar manner. So I'm going to actually do some problems before I explain the whole reason why what I'm doing works. But hopefully as we work through the problems you'll see kind of how things are fitting together. In this first example, so we've got this kind of ugly looking integral, and the substitution we're going to use to start out with is a very different kind of a substitution. So this is what's known as our trig substitution. So we're going to have x equals 5 sine of theta. Okay, and we'll get into later why that works, but for now just accept that that's what I'm going to use. Now one thing you'll notice is very unusual is usually when we've made a substitution in the past, our substitutions have looked more like, a w equals something with an x in it. So usually, we're replacing stuff with the x's, and that's not what we're doing in this problem. Okay, this time we're actually going to replace the x with something with a theta involved. And why theta? Because we usually think of that as an angle. It is actually sort of an angle substitution that we're putting in. It may seem very odd. Why would we put in trigonometry in a problem where there's no trig? That seems to be making things worse. But I promise you it will make things better. Okay? So this is going to be your substitution. Everywhere we see an x, yep, we're going to replace it with a 5 sine of theta. And of course, the other thing we have to do is, if there's an x, there has to be the dx as well. And so the dx will be our derivative of this, 5 cosine theta, d theta. And so that 5 cosine theta d theta will replace that term. All right? So as we rewrite this entire integral, we will have the integral of, now the top part is the dx, is now 5 cosine theta d theta. In the bottom, we have our x squared, which is going to be this squared, or 25 sine squared theta. All right. And then our square root of 25 minus x squared, and again, doing the substitution, that becomes 25 sine squared theta. All right. Lengthen that out, and I think you'll all agree we certainly made it look a lot worse. However, it gets better. And here's how it gets better. One thing to look at inside the square root, the problem with the original integral really has to do with that square root. Square roots are horrible to deal with. And so what we're going to be doing is we're going to concentrate on what's in the square root. Okay? Now notice each term inside the square root has a 25 in it. Well, so we could actually factor out a 25. And so really it's a square root of 25 times the square root of what's left if I pull out the 25. Well, this will be a 1 minus 1 sine squared theta, or just 1 minus sine squared theta. Well, where have we heard 1 minus sine squared theta before? Well, that's one form of our standard Pythagorean identity. 1 minus sine squared theta is cosine squared theta. So that square root becomes the square root of cosine squared theta. Right? So we have that square root of 25. Well, look at these. Perfect squares. Square root of 25 is 5. Square root of cosine squared is the absolute value of cosine of theta, but we're not going to deal with negatives here. Okay? We are actually going to restrict ourselves to just dealing with positive stuff in our substitution. And there's some reasons, detailed reasons why we can get away with that, and I'm not going to worry about it too much. Okay, so you don't either. Just know that we're going to do this. It's going to work. So everything we did with the square root now gets rid of the square root. Okay. So again, let's try to write down what we have. So the numerator is still the 5 cosine theta d theta. Okay. Our denominator, we have our 25 sine squared theta. And the square root is now just this piece of the 5 cosine theta. And now our 5 cosine thetas cancel top and bottom. Yeah, isn't that nice? So we now have this integral d theta 25 sine squared theta on the bottom. And just a little rewrite there. Pull out the 25 in that denominator out front. And 1 over sine squared, well, that's cosecant squared theta. Okay, and you're supposed to know the derivative of what is cosecant squared theta? The derivative of negative cotangent theta. And we still have our 1/25th and plus c. Now, normally you'd say, okay, we're done. We figured out the antiderivative. But like any substitution, we have to say, but we did a substitution, so we have to put the theta back in. Now here, I don't want you going and saying, oh, let's solve this for theta. That's just going to be ugly. Okay, we're not going to solve that for theta and then plug this in. It's just not going to give you a good answer. We're going to take a different technique here. And the technique we're going to use, just a moment here, we're actually going to think about what did this substitution do that we originally came up with here. So original substitution of x equals 5 sine theta, I said it was related to an angle here, right? Or a triangle, in fact. So let's just think about we have some triangle. Okay, and I'm going to label this triangle to represent the substitution we actually have here. So in our substitution, we said, well, if x is 5 sine theta, another way of saying that is the sine of theta is x over 5. So I'm going to label one of these angles, so this is a right triangle, by the way. So one of these angles, theta, from our substitution. And so if the sine of theta is x over 5, that will be opposite over hypotenuse. So the opposite over hypotenuse being x over 5. So this triangle represents the substitution. So now if we take a look at what do we have in our final answer, well, I have a cotangent to deal with. Well, how do I find the cotangent from this substitution that we're making? Well, just looking at the triangle, well, a cotangent of theta is going to be adjacent over opposite. Well, how do I find the adjacent here? I don't know that one. Well, a Pythagorean theorem will do that, right? It'll be a 5 squared minus x squared, or 25 minus x squared. Now, getting the square root of 25 minus x squared shouldn't actually be surprising if you think about the original problem. We started with the square root of 25 minus x squared. It shouldn't be surprising that we end with it. So our cotangent being the adjacent divided by the opposite. So that goes in here. And so multiplying that by the made a little mistake here. The opposite there is not a 5. The opposite there is an x. Okay, so now we plug it in. It's negative 1/25. Our cotangent is our square root. Oops, sorry about that. Square root of 25 minus x squared over x and plus c. So this final thing is the correct working out of that integral. So we'll try another one here. I think I'll switch to another video.